I'd like to extend a warm welcome to all of you and thank you for tuning in for this Associated School of Construction conference paper presentation. The title of our paper is Construction Cost Predication Model Using Macroeconomic Indicators. Our research is focused on building a model to reliably predict construction cost indices based on economic indicators and neural network design using group method of data handling. This paper shows that reliable forecasting to estimate cost of construction can be built using economic indicators, a priori data, and the group method of data handling type neural network. Estimation of future costs of construction is important to any success of a contracting company. Investment decisions can also be supported by accurately forecasting construction costs and can allow maximization of profits. Cost adjustment techniques do exist using cost modification, and these are basically stochastic in nature based on past experience and are linear modifiers. Traditionally, cost modifiers have been utilized given the recent data on inflation, construction market that's impacted by the economy, and weighted averages of various building materials. We set out to prove by this research that it's possible to estimate the future cost of construction based on historic cost and macroeconomic indicators. The objective of this paper is to find the correlation between and predict future costs of construction based on the historic cost data, which is found in data that's been in a database for construction and building cost indices, and economic indicators, basically the leading, lagging, and coincidence economic indicators. The first variable that we use in this model started with the third quarter of 1978 and runs through the third quarter of 2018, and it's the leading economic indicator. The LEI reflects the degree of stability in the labor market, the amount of orders that new products and future production that is in order for the present time, material prices that reflect shortages or surpluses of raw materials used in construction, consumer spending, and it's a basic general gauge for the near future of the economy. The lagging economic indicator was a second variable that we used in our model. It is affected by unemployment in the labor market, the burden of paying back loans, interest payments on production and consumer services, also the cost of maintaining inventories, and it's a general gauge of the near future of the economy. The coincident economic indicator was the third independent variable that we used to construct our model. It mostly relies on non-agricultural payrolls, the industrial and manufacturing market, the effects of employment and labor, real income from production and manufacturing, trade sales, flow of goods, profits from mining and manufacturing, and it reflects the most current state of the economy. The construction cost indices and the building cost indices are measured by common labor hours, the 200 common hours from a 20-city average over common labor rates. And the building cost index has been used historically from estimating from skilled labor sets, 66.38 hours over a 20-city average for bricklayers, carpenters, and iron workers who are considered the most skilled laborers, and other construction products that are needed, steel, cement, and lumber being the three most important ones, and the 24 count weights of hundreds of products for steel, 1.1 tons of cement, and 1,000 boards of 2x4 lumber. So when we put the historic costs together for the cost indices of construction and also the economic indicators, we see that the construction indices run a lot more linear than what's going on in the economy, which is a more nonlinear and not as predictable. So our idea was to try to put the economic indicators into the construction cost estimation model. So this paper establishes the basis for reliably forecasting the construction cost indices using a predication model based on the leading, lagging, and coincident economic indicators added to the neural network as independent variables. Historically, we can design linear regression models for the building and construction cost indices. If we want to follow through and try to build a method that's more nonlinear, we would have to prove the stationarity of the data. So this was what we did first. We took the first derivative of the data, we added a polynomial fit to the data, and then plotted it. And you can see here that we do have the first derivative test proof of the stationarity of data. The regression analysis and neural network for the predictive model are based on a Levenberg-Marquette neural network model and a basic backpropagation model. We start out using linear regression as a baseline for weighted parameters, and we extend that to use activation functions at each of the nodes, internal and the final layer of the network. And then we also add the Levenberg-Marquette technique, which uses a damped least squares method for minimizing error. So the feed-forward network for a basic group method of data handling neural network would use nodes in the middle that actually optimize the coefficients for those, and then we add the nonlinear activation function in each of the nodes in the output. So I1, I2 in this case would be the economic indicators, and then the output for P would be one of the construction cost indices. So this is just an example of how the network works. And then a polynomial equation is derived for each of the building and cost construction indices. And these are based on the past components for X and I, and then the multivariate analysis of both of those joined together. A, B, and C are weights or coefficients, and the output Y is the response of the system, or in our case, it would be either BCI or CCI. This first result shows the backpropagation neural network model for BCI based on LEI. It also shows the error in the lower graph. The error is well tolerated under 100 for most cases, and that would mean 100 over the range of 2,500 to 6,500 at the max, which is less than 2%. We can see that some of the tested values still have very low error. The training network matches the original data almost exactly, and the validation outputs to very close and very low error. If we look at the Levenberg-Marquette model, we see that it's a little bit closer and has slightly better results because of our error function uses a damped least squares error model. In our predictive model, we can see that we do have some error, but this is based on some new data and also a linear regression model we think that the model that we have in the CCI for this neural network is a higher predictive model. This graph shows the model that we used for the CCI based on CEI with a coincidence economic indicator with backpropagation. Again, the error is very low. And as you could see, the test outputs and the validation outputs follow the curve almost exactly, so that the network is well trained. And then this is the CCI based on the response and tests for all the EIs. And that one is also very close to our actual data. And then we have a prediction model. Again, we used it against the autoregressive model. And so these are basically showing the differences between the two. We also show here in the error that in this histogram that the error is also very low. And again, you know, we're looking at data that's from 3,000 to 11,000, and the error is less than 100 in almost every case. Only one case we had higher than 100 for one of the training sets. So this study was designed to discover if there's a distinct correlation between CCI and BCI to the macroeconomic indicators, which are the leading, the lagging, and the coincidence economic indicator. Trends can be predictive for future economic assessment, and that the error associated with these predictive analyses is reasonable, so that the model can be used reliably for future economic forecasts. Thank you for attending this presentation, and we hope that you have more interest in this analysis.